And here it goes. Welcome, everybody. This is episode 2 of the Bespinian and Vision series of GitOps webinars. We are Thursday, May the 6th, 2021. It is 4 p.m. Central Europe Daylight Saving Time. My name is Adrian Kosmaczewski. I'm Developer Relations at Vision, and I will be your host tonight. And of course, it is my privilege to once again introduce you to the real stars of the event, Lena Fuhrimann and Mathis Kretz from Bespinian, a company in Bern, Switzerland, specialized in Kubernetes, DevOps, all things cloud. And those of you who are Star Wars fans, of course, undoubtedly recognize the reference in both the name and the logo of Bespinian. I will not say which of the movies. I'm pretty sure you know which one it is. So that's really cool because it was May the 4th this week. So it's totally appropriate to make the reference. Previously on this series, we learned the most important concept about Git, how to use it effectively. So if you haven't watched it, check it out. It's available on YouTube at the URL that you can see on the slide, which is bit.ly/GitOps episode 1. And basically, I gotta tell you, it's much, much better than the episode 1 of that same series that I just mentioned, which is Star Wars, okay? So please check it out if you haven't already. The link will be as well on YouTube because we are recording this as well. This will be as well on YouTube. But today is the second episode. And again, it will be much better than the second episode of You Know What. And we're going to build on top of the previous knowledge about Git. We're going to learn about infrastructure as code and how it can help DevOps teams work better and to be more effective. And Lena and Mathis are going to talk about Terraform, Packer, and plenty of other tools that are very, very interesting, and they are very active on this field. So without further ado, here is Lena and Mathis from Bespinian. The stage is yours.
Thank you, Adrian. I will take over the screen. Can everybody see what I'm sharing?
Yes.
Good, thank you very much. So, welcome friends and future friends, also from our side, to this second part in our webinar series about Git and GitOps. Today, we'll look into a topic that is crucial to any modern cloud-native environment in order to provide stability and parity across environments, infrastructure as code. We'll delve into some interesting tools in that realm and compare different concepts and configurations around how to deploy and maintain infrastructure in a sane way. At the end of the presentation, you'll have a good understanding of IAC and its benefits, and you'll have a mature tool set available in order to implement it in your team. But before we dive into some technical solutions and frameworks for infrastructure as code, let's first examine what we mean by the term. Or actually, let's start off by looking at what we would not call infrastructure as code. While certainly being awesome in their own right, we would not consider as infrastructure as code tools like Ansible, Puppet, or Chef, which allow you to apply configurations to existing VMs. The reason for this is that these tools generally do not take care of the VM or resource creation step, which, as you will see later, we consider an important part of infrastructure as code. That said, tools for VM configuration certainly have their place in DevOps, as we will see later when we have a closer look at Packer. Furthermore, we would also not consider imperative scripts, which create VMs and possibly install things on them, as infrastructure as code. This is because we consider declarativeness as an important feature of infrastructure as code, as you will also see later. So what is infrastructure as code then? Similar to source code, which, when unchanged, produces the same binary every time it is compiled, infrastructure as code mandates that the same model, given as code in a textual format, always generate the same environment. Furthermore, it generates the environment automatically without the need for manual configuration or installation steps. On the slide, you can see an example of a VM described declaratively, in this case in Terraform syntax. You will learn more about Terraform later in this webinar. You can see that we specify a name and a type for the VM. Furthermore, we also state the availability zone in which the VM shall be created and a security group to which it will belong. The latter two parameters are not hard-coded in this particular declaration, but instead they are referencing other resources in the environment declaration. In the case of the availability zone, we are referencing a variable declared elsewhere. And in the case of the security group, we're referencing a security group declaration made as a separate resource. Having the possibility to reference resources and resource definitions and their properties in other declarations is very important to infrastructure as code, as it enables us to modularize our environment declarations and avoid repeating ourselves when building variations of our environments. So why would you want to have infrastructure as code? Here are the most important reasons. The first reason is that it prevents environment drift. If you have environments which are automatically generated from code, no one should be able to introduce undocumented changes to a particular environment by manually making configurations on some VM or some virtual network, for example. This means that your application will not suddenly break when transitioning from, say, the test environment to production, for example, because there are some infrastructure tweaks which were only made on test but not on production. The second reason is that infrastructure as code prevents snowflakes. By snowflakes, we mean infrastructure configurations which have evolved in an intransparent and often undocumented way, along with some deployed applications. It is often impossible to recreate the same configuration on a new infrastructure without repeated trial and error, essentially replaying the evolution of the initial system. Having your infrastructure generated from code will ensure that the evolution of your infrastructure will stay documented and that fresh rollouts will contain all changes introduced as part of this evolution. The third reason is that infrastructure as code enables you to version your environment declaration in a version control system like Git, which we covered in episode 1 of this webinar. This has the advantage that you may use the standard features of version control to manage your infrastructure. You can use the commit history to find out why and when a particular infrastructure change was made. You can use diff to compare two states of your infrastructures, and you can use merge requests to implement a review and approval workflow for infrastructure changes. The fourth reason is that infrastructure as code gives you a reproducible and deterministic way to spin up as many instances of your infrastructure environment as you require. This obviously gives you more flexibility and makes people feel more confident when making changes. The fifth reason is that by writing declarative infrastructure as code, you automatically document the created environments. By automatically applying this documentation, we know that it is always up to date and gives us an easily readable description of everything that we have deployed. So now that we know what infrastructure as code is, let's dive a little deeper into some of the guiding principles which make it work. These principles allow for our source code to be the only source of truth and for us to get the maximum benefit out of infrastructure as code. The first important principle of infrastructure as code is being declarative. But what do we actually mean by that? When communicating with systems of machines, it is intuitive that to procedurally describe the operations which we need to perform in order to get from one state to another. This is what we call the imperative style. When doing so, you're saying things like, first create a VPC, then create a new VM, then create a new Kubernetes cluster, then install Linux on the VM, and so on and so forth. The opposite of imperative is declarative. A declarative representation of your infrastructure describes a desired state which you want your environment to be in. A declarative representation says things like, there is a VPC, there is a VM, and there is a Kubernetes cluster. It does not say which steps need to be undertaken to get from the current state of your environment to this new desired state. So why do we prefer a declarative style over the imperative one when automating infrastructure? If we think more deeply about our imperative example, we see that there are a lot of cases which our script needs to catch in order to function correctly. What if a VM with the same name already exists? Do we stop? Do we do something to the existing VM? Or what if the creation of the VM takes a long time? What happens if the script fails halfway through? Can we just run it again? All of this reasoning about special cases, potential failures, and long-running asynchronous processes is abstracted away if you use a declarative style. In the declarative style, you just describe a desired state and leave it to your infrastructure as code technology to figure out the steps required to get into that state. This makes declarative representations of infrastructure a lot cleaner and easier to reason about for operators. Another advantage of declarative representations is that it's always clear what the desired state is, even in a case where the state of your infrastructure changes due to failure of one or more components. In such a case, an infrastructure as code technology will use this representation to bring your environment back to a desired healthy state. Declarative representations have an obvious downside. They make the job of a particular infrastructure as code technology a lot more involved. Technologies which support it need to have a way of determining a given current state of your infrastructure, figuring out the delta to your desired state, and then applying the right operations to close the gap. Later in this episode, we will introduce Terraform, which features just this kind of declarative representation. The second important principle for infrastructure as code is idempotence. This means, according to Wikipedia, that a configuration can be applied multiple times without changing the result beyond the initial application. Or in more technical terms, a function or operation is called idempotent if it produces the same results regardless of whether it is applied just once or many times in a row on any input. In infrastructure as code, idempotence generally makes an operator's life easier, since it enables them to ask the infrastructure as code technology for a specific desired state without having to know the details of the current state of an environment. Indeed, infrastructure as code technologies which are based on the declarative representation of a desired state are automatically also idempotent. Stretching the definition of idempotence a bit, we usually also mean that when applying a desired state declaration to an environment, infrastructure components which already conform to the desired state are not touched. Again, this makes the life of operators easier, since they can rest assured that no components will be interrupted unnecessarily due to a change in desired state. The third important principle of infrastructure as code is that all infrastructure is disposable and can be recreated at any time without manual intervention. The admittedly somewhat cruel analogy being that infrastructure is treated like cattle. Long-living components, which are manually maintained and updated by operators, would be considered as pets by the same analogy, and are not suitable for infrastructure as code. Having disposable, fully automated infrastructure has the advantage that we can painlessly try out and change things without worrying about breaking manually maintained pet components. So, for example, if you have a server which you have given much love, where you have installed and configured things manually, maybe you've even given your server a name like Lenny, and if Lenny were to die, you would cry and be very sad, then you have typically created yourself a pet. If, on the other hand, you have a herd of servers which serve a purpose, but which can be recreated at any time without manual intervention, then you're dealing with cattle. The fourth important principle of infrastructure as code is that there is a pipeline in place which is capable of continuously propagating the current desired state through to your various environments. This also mandates that automatic tests are performed on infrastructure level. We will see later how such tests are achieved. Being able to continuously enforce a desired state based on a declarative representation of your infrastructure in Git will actually be the topic of the third episode of this webinar trilogy. So we won't go into more detail just yet, but be sure to join us for that third episode. Now that we have the theoretical knowledge around infrastructure as code, let's look a bit more into how we can actually apply it and which tools can be helpful in order to manage your resources in a sane way. And for that, I'm happy to hand over to Lena.
Thank you, Jesus. So I will also share my screen. And now you should be able to see the first slide, right?
Yes, perfect.
Okay, good. So first off, there is the open source tool Terraform, and it has become pretty much the de facto standard tool for managing infrastructure in a declarative way. It is an independent tool created by HashiCorp, so it's completely infrastructure provider agnostic. And that means that it can work with many different resource types. However, it does not mean that you can simply switch back and forth between the providers to prevent lock-in. So a VM that you have created for AWS, for example, cannot just be applied to Azure or Google Cloud. And this means that you can write Terraform code with any provider and even combine them in a single module, but individual resources are highly specific to that provider, and they cannot just be switched out because a VM in Azure might require different parameters than one in AWS. Terraform itself is very modular, and the individual modules and providers are maintained by a huge and active community. And this makes this tool always up to date, and new features that the infrastructure providers introduce are usually available very quickly. The best example is the AWS provider for Terraform, which gets updated multiple times every day and very much keeps up to date with the fast pace that AWS has when it comes to releasing new features and products, and still it does all that while being very stable in terms of not breaking your existing infrastructure configurations. For its resource definitions, Terraform uses its own language, which is called HCL, or the HashiCorp configuration language. And this means that new users of Terraform have to learn this new language. But once they know it, they can apply it to any infrastructure provider there is. A second category of tools are the ones maintained and released by the larger infrastructure providers themselves. And as an example here, we took AWS CloudFormation, which is Amazon's infrastructure as code tool. However, there are many very similar tools for Microsoft Azure, so the Azure Resource Manager, and for Google Cloud Platform, the Google Cloud Resource Manager. And these tools are always specific to the respective provider. and they don't let you combine the resources with ones from other providers. Furthermore, they're usually not maintained by an open source community, but rather by the providers themselves. Surprisingly, most of the time, Terraform is more up to date with newer features than the tooling that the infrastructure providers themselves maintain. So that is a big yay for open source. If you prefer to write actual code instead of just configuration files, then Palomi might fulfill your taste. It supports multiple programming languages like JavaScript, TypeScript, or Go, .NET Core, and Python. And it lets you declare your infrastructure as actual programming code. This may go a little bit against the declarative approach that Thies talked about before, but usually the Palomi library encourages code that actually looks quite declarative. And the great advantage of such a tool is that you don't have to learn a completely new language because you probably are already familiar with one of the ones I mentioned before. So you can use all of the existing tooling and ecosystem around your favorite language, like for example, linting or even type checking, if your language supports that. So your text editor or IDE can help you with auto-completion, tell you if you use a number where you should have used a string, and so on. Furthermore, you can use all of your language's features, like loops and if statements, to make your infrastructure setup more intelligent. The downside of this is that you can make the code quite complex and actually make it hard to test and use. So now let's take a deeper look at Terraform. As mentioned before, it has become somewhat of an industry standard because it's quite intuitive and it has a lot of powerful tooling around it. It's also quite versatile, and that's why we want to use it to introduce a couple of building blocks of infrastructure as code around it. The first building block or concept is what Terraform calls a provider. And since it supports many different infrastructure providers, and each of them is maintained and managed by its own community, users need to be able to plug different providers into their setup. A typical provider could be AWS or Azure, or even Cloudflare or Kubernetes. These contain and abstract the domain-specific knowledge necessary to communicate with the respective infrastructure provider, and how to translate different operations on different resources into API calls towards the respective provider. So for example, the AWS provider contains knowledge about how to provision a VM in AWS, but also how to configure it, how to change it, and how to delete it if the respective resource in Terraform gets deleted. And this modular provider setup is a big part of the success of Terraform, since it makes it an incredibly versatile and powerful tool, which can be used by different communities and even combine infrastructure from different providers into one single code base for its end users. So let's quickly see how such a provider looks in code. So I'm going to use the example of the repo of the Bespinian website, bespinian.io. Here, if I open this repository, then I can see that it has an infrastructure folder. This contains many Terraform files. And if I look at the main TF file, then you can see that it has different provider blocks. Now here we are using exclusively AWS providers, but we could also introduce Google Cloud or Azure here to have a more versatile setup. Another important concept for Terraform are modules. And as the name implies, they allow us to modularize our infrastructure and create layers of abstraction. A module is any set of Terraform resource definitions that belong together and are life-cycled as one. Again, let's look at an example. This time, I will go into a repository that I have created which is called Terraform single page application. So this is a Terraform module that allows you to host a single page application on AWS infrastructure, so on S3. And if we look at that, it again has a main.tf file. And what is important is it has a variables.tf file, which defines which variables I can specify for this module to be configured. And I can use those to parameterize it. Also, it has an outputs.tf, which tells me the different output variables that this module generates. So if I'm using this module, it's kind of like using a specified function in a programming language. It has a couple of inputs, which are the function parameters, and it has a couple of outputs. And in the middle, it does something, in this case, to our infrastructure. So as this repo shows, modules allow us to make our code reusable. And Terraform itself actually has a huge registry of such modules for many different providers. And usually it is recommended to use them wherever possible because they help us to write less code, follow best practices, and actually automatically keep up to date with changes from the infrastructure providers. You can find all of those at registry.terraform.io. Another important part of modules is that they allow us to test parts of our infrastructure. Now, testing our infrastructure might sound quite weird, but we will talk more about that later. In Terraform, the so-called state is another concept, and it describes all of the provisioned resources in our infrastructure and how they are configured. And it does that in a simple and human-readable way in one file. This means that we always have a single file that describes the current state of all of our infrastructure and the configuration of each of its resources. When changing something in the declaration of our modules or resources and then applying these changes, Terraform first makes the changes using the respective provider and therefore talking to the actual infrastructure provider's APIs. And afterwards, it updates the state file to reflect the respective changes. Let's have a look at such a state file. As you can see, it's just simple JSON, and it contains one object per infrastructure resource that I have, and it defines all of the different resource parameters that we have there. So it's quite easily readable for humans, and it allows us to see at one glance what our configuration is. Now, there are different places where we can store state files with Terraform. The simplest one is the one you just saw. The file can be checked into Git and be versioned with the application. However, this has two downsides. The state file can change after a deployment. So if we do CI/CD and our CD server changes something about the infrastructure, then the state file also changes, and we have a dirty repository. And the second downside is that it doesn't really allow for multiple people or systems to apply Terraform configurations at the same time, because they might actually have different state files locally, and this will eventually lead to problems. Therefore, usually it's good to store the state in a central location, like an S3 bucket or even the Terraform cloud. Terraform supports many such different backends. For example, you can also store it on Google Cloud or Azure. That's no problem. But what happens if people change resources manually without actually using Terraform? Or even if they create resources that are then not managed by Terraform? This is what we call infrastructure drift. And it means that the actual state of the provisioned infrastructure has drifted from the state stored in Terraform. This is a major problem with any declarative system and can only be mitigated by either trusting people not to do so or by preventing it by simply not giving them right permissions in the important environments such as production. However, that is not always an option. There is a very useful tool called driftctl, which allows us to detect infrastructure drifts and tells us which resources are not managed by Terraform or which ones have changed in their configuration state. So let's do another demo and see how that works. Again, if I am in the bespinian's infrastructure folder and I run drift control scan, then what drift control does, excuse me, is to actually scan all of my existing infrastructure. And in this case, it found quite a lot of infrastructure resources that were actually not created by Terraform itself. It didn't detect any resources that have changed and that are managed by Terraform, but the ones that you see here are ones that have been created without using Terraform. For most of those, we did that intentionally, but some of them we should actually clean up, which this tool helps us to do. So now let's put our knowledge to work and have a look at a typical workflow using Terraform. First, we initialize the repo, which tells Terraform to download the respective providers and modules. And this is important to have a clean local state and to be aware of the current remote state. Excuse me. The upgrade flag tells Terraform to look for dependencies that can be upgraded within the allowed limits. So for example, we can restrict that providers are not upgraded beyond their major or minor versions. The second step is then to do our actual changes. In this case, we just use Vim to edit one of the files, to maybe add a new resource or change an existing one. It can be it can be useful to lint certain configurations in our Terraform definition. And this can prevent application failures from happening in the first place and help you to follow Terraform and provider best practices. Two of the most popular linters are firstly tflint, which is a general linter for Terraform code, and it also supports AWS, Azure, and GCP resources. A second very popular linter is called tfsec, which is very much focused on security and preventing security holes in your infrastructure. It is therefore highly recommended to run these two regularly or even make them part of your CI/CD process. As a next step, we run the command terraform plan, which does a comparison of the current infrastructure state and what we are applying. So it gives us a very nice diff of what would change if the new configuration were to be applied, so that we can verify that none of the changes are actually unintended ones. As a last step, we then finally apply the plan changes by running Terraform apply. This may take a while because it now actually talks to the infrastructure provider's API to provision or change the resources as specified. Afterwards, as I said, our state file is updated and the configuration has been successfully applied. Obviously, it's pretty tedious and inconsistent having to apply all of these changes done to our repo manually. So like any other deployment, we want to automate these steps and leave them up to a CI/CD server, which maybe runs in a consistent environment and reliably creates consistent deployments. Theoretically, this can be done with any old CI/CD system where the Terraform binary can be installed, because it just needs to be able to read out the credentials and run Terraform apply. However, there are useful modules for the most common systems, which simplify this process even further. For example, there's a pretty versatile GitHub action to use Terraform commands, which you can see here on this slide. And you can also see that it follows exactly the steps that we had discussed before. It does an init, a plan, and then an apply. Since infrastructure can be modularized with Terraform, it makes sense to test these individual modules, just like we write tests for the individual functions that make up our applications. Firstly, to make sure that they actually work, and secondly, to verify that their interface is clean and it provides everything that one needs to use them properly. One tool to do this in an automated way is called TerraTest. And it allows us to write simple Go code, which then calls Terraform under the hood. It temporarily creates the infrastructure contained in our module to see if the configuration is valid, and then runs a couple of tests on it. As soon as all of the tests are through, the infrastructure is then automatically deprovisioned and deleted again. So this is the flow that it follows. Again, let's see how that looks in practice. So before, we were talking about the Terraform spa module that I had created. And if we look at that, then it has a test folder, which contains a simple Go file. For those of you who can read it, this should be quite familiar. For those of you who can't, that's not a problem because it just is quite easy to read actually. So what the file does is we can set some Terraform options, and then down here, as you can see, it just does a Terraform init and apply. Then it, once the infrastructure is applied, it does some assertions. So for example, in this case, it checks if the fully qualified domain name that has been used by the module is the one that we actually expect. And then by using the first statement here, it destroys the resources again, so that we have minimal cost. And I can now apply this test by simply writing go test. Okay, I guess in this case, it's not ready, but usually I could just run go test now, and this would actually deploy the infrastructure, run the tests, and tear it down again. So as you saw, this creates actual resources in our environments. So it is crucial to wait for the cleanup to happen and to be aware of the costs that this can result in. The resources themselves, they are very short-lived, but nevertheless, they can be costly. Furthermore, sometimes the cleanup can fail. And that is why it's important to run the aforementioned drift control tool from time to time to check for remnant resources that need to be cleaned up manually. Obviously, it is also very important not to run these tests in a productive environment, because even though they shouldn't, they can sometimes interfere with existing resources if they're not implemented correctly. But all in all, these tests help greatly to have a stable infrastructure and to be more confident when releasing new versions of our modules. So we think it's very important to have them, and also obviously to maintain them well. Another concept that we quickly want to look into today is called immutable infrastructure. It is another good practice around infrastructure as code, and it simplifies the management of large fleets of VMs and other resources. The idea behind immutable infrastructure is that we can create infrastructure, for example, VMs that then cannot be changed at runtime. So if we want to update, for example, the base operating system of our VMs, then we don't log into each of them and run the update command, because nobody would do that for containers, right? Much rather, we should just follow the good practices we have learned from containers and create a new VM image with the new version of the base OS, and then actually restart all of our VMs or even recreate them in a rolling upgrade with the new image. And a tool that helps us greatly to simplify this process is again from HashiCorp, and it's called Packer. it allows us to define our VM images just like we would do it with a Docker file for container images. So we have a configuration file which contains a base image and then steps that should be applied to it. Packer then takes these instructions, creates a new image that contains our application and all of its dependencies, and then publishes that image to the infrastructure provider's image registry. This process allows us to follow all the good practices of shipping images, which we are used to from using containers. Like, for example, shipping them with all the needed libraries and binaries and not changing them at runtime. But this time, we apply these concepts to VM images and treat our VMs kind of like containers in that regard. Obviously, this has many advantages. It expedites the startup of our VMs because we don't need to install hundreds of tools and packages when they start up or when they get created. And it makes our images and applications more portable and testable because we can actually release the same image using Packer to AWS, to Google Cloud, and also to our local virtual box, for example. These processes should also further improve the stability and the resiliency of our environments and VMs, because no undocumented changes are allowed, and all of the steps needed to get to our final images are documented in the Packer file. Again, let's see how that works in practice. I've prepared a little demo. And as you can see, it just contains two files. One of them is the actual Packer file, and the other one is a shell script. If we look at the Packer file, then you see that we can define variables up here, and then we define the from image. In this case, I'm just using Ubuntu, as you can see here. So the latest Ubuntu Xenial 16.0. And then down here in the build steps, I'm saying that this should be my from image, just like we do in a Docker file. And then I can add different parameters, which then apply steps to this image. In this case, I'm using the shell script of different single shell commands, stuff like that. Usually Ansible can be used here quite well. And if we look at the shell script itself, then all it does is it installs Nginx on this VM. So now if we run Packer build on this, then that actually spins up a VM in AWS. Again, I haven't cleaned up my previous one, so it doesn't work, but usually it would now spin up a VM in AWS. Then it would run the instructions. It would take a snapshot of that VM and then create a new image out of that snapshot. So this was all of the concepts that we wanted to introduce. We thank you very much for listening. The next episode of the webinar will be about GitOps, as already mentioned, and it will take place on the 8th of July. Thank you very much for listening. We are now open for questions.
Thanks, Lena. Thanks, Mathis. And actually, we have not a question, but we have a comment from Gerald Crescione, who works apparently in the driftctl team. So he's very happy that you mentioned driftctl during the webinar. So that's really, really cool. Thanks, Gerald, for attending. Thanks to you for being there. I don't see any open questions, but of course, feel free, maybe somebody's writing them down. While you write them down, while you write your questions down, I'm just going to show one last slide. Write down the date and time of the third episode of this GitOps webinar series. It will be on Thursday, July the 8th at, again, 4 p.m. Central Europe time, daylight saving time. And of course, this episode that you just saw is going to be available on Vision's YouTube channel, vision.tv. So make sure to subscribe and to be notified of the update of this video. And again, I'm just going to take a quick look to see if we have any questions. I don't see any. So in that case, we move forward, and thank you so much, Lena and Mathis. Fantastic once again. And thanks all of you who joined or who are watching this video right now on YouTube, wherever you are, whenever that is. And see you on July the 8th, 2021 for the third part of this webinar, which will aptly named GitOps, as it should be. So great. Thank you, everybody, and see you soon.
Thank you, everyone.
Thank you very much. Bye.
Bye-bye.